New topic, but quite a lot of the same type of mathematics involved. So seismic subsurface imaging. And in today's talk, I'll spend most of the time developing a model for scattered acoustic waves in the subsurface of the Earth. And I talk at least about setting up the problem of extracting singularities in the sound speed, the acoustic waves, or the pressure waves that are traveling in the subsurface from measurements of the scattered waves. I suspect that I will run out of time towards the end, once I start coming on to imaging, but I'll just save it for tomorrow in that case. Okay, so here's a cartoon of the subsurface of the Earth. Here's the surface. Don't really think of it as a boundary. Think of it as just an artificial boundary with the air continuing on up above. Little asterisks are sources, and triangles are geophones, recording instruments. So again, you can build in some more detail into the sources of acoustic waves. I will take simply punctual point sources for simplicity, like we did in the radar, but you can build in more details about the temporal signal that's sent, and even if it's sent over an array of transducers as well, that could be accommodated. So if you set off a source, an acoustic source, you would get these spherical waves, even though I'm drawing it in 2D. You should really think in 3 dimensions. And so you get these spherical waves which will travel and possibly bend and deform the wavefront. And then they'll encounter some change in different types of rocks, say for example, or water, salt, so forth. And that change in material properties will cause a wave to scatter. So while I'm on it, the criterion basically for scattering of waves, a wave will tend to scatter as soon as it impinges on some material properties which are changing on a scale that is smaller than the wavelength that's being used in the source wave. So you get these scattered waves, which hopefully will come back up, and you listen for the echo of what you sent on the geophones. So you've got this excess pressure field, really, that apart from the atmospheric pressure, you measure the excess pressure field that arrives at the geophones. There are all sorts of fancy geophones now. They have electrical coils, and you get 3 dimensions if you want to measure actually displacement, if you were doing measuring elastic waves. But we'll just do the simple scenario of pressure waves. And the inverse problem is to try and extract the sound speed that went into making these pressure waves and determine what the high frequency changes are in the sound speed. Or figure out where these scatterers are. Okay, so I'm thinking about these as being little interfaces between 2 different types of materials. This is a famous synthetic model called the Marmousi model. And it's supposed to incorporate all sorts of features, strongly refracting high salt domains and pretty steep dipping interfaces. And so this is the actual model, or a section of it. I haven't shown the data. I'll show some seismic traces in a few minutes. But if you run the proposed type of back projection algorithm like what we saw in radar, this is the reconstruction. And it's so-so. Right? There's a lot of stuff that's not being recovered. You can see there's some problems going on here. And hopefully by the end of the talk, end of tomorrow's talk, you'll get an idea as to why that type of deficiency is there. There's a lot of high changes, smooth, high contrast in a smooth sense, which will cause waves to focus. So there's a lot of strong refraction going on that leads to problems in the reconstruction. Okay, so a lot of these diagrams, I haven't said it, I just suppose I'm used to thinking about these numbers across the top. You would set some origin, say if it was a two-dimensional scenario, which this actually is. You have some origin, and these are distances from the origin to the current receiver location. And this is time in the vertical axis, usually measured in milliseconds. So this is just it's been windowed in time from 700 to 2,900 milliseconds. Okay, and then just from maybe a subset of the receivers. Yeah.
Do you not take care of the reflection explicitly?
How do you mean
it's like in your modeling, you must be taking reflection into account, or does
yes.
it assume straight path? It must be if you're taking.
Yes, when I say the acoustic model of Earth, I'm just about to develop a model of reflection. Yeah. Okay, so let's suppose that the speed of propagation in the subsurface is described by a field C of x, like it was in the radar example as well, same type of notation. And we have a source located at S. Then if you measure the propagating field at location, subsurface location x and time t, then it obeys the scalar acoustic wave equation with a punctual point source. Right? So to say, set off an impulse set off at time equal to 0 at location concentrated at x equal to s. Right? Going back to the picture here, one of these s's. Okay. And it's causal. Okay, so we'll assume that the pressure field is 0 for negative time. There's no boundary. Okay, the reason why I'm not dealing with the boundary is eventually we'll be windowing this in time, and I can pretend that the waves can go on in free space forever. Okay, so there is a map which takes the speed in the subsurface to our pressure measurements. So this is the pressure measurements due to a source at location S, measured at a receiver location, one of those triangular geophones over on the left-hand side of the cartoon, at time t. Okay, so we set off the source S and we listen at this receiver location, or at time t, and we listen to one of these seismic traces, of which I'll show you one in just a few moments. The source and receiver location are completely general. I'm just going to say that they belong to a submanifold of this surface of the surface of the Earth cross the surface of the Earth. So the pairs of sources and receivers are allowed to lie on a general submanifold of the surface cross itself. I'm just wondering, does it sound okay? It sounds as though my voice is cutting out every now and then from the microphone. Does it sound consistent?
It's okay.
Okay, yeah. Okay, thanks. Okay, so this is the set of sources and receivers. I will refer to it as the acquisition geometry or acquisition manifold. More properly, I suppose, manifold. Okay, so sigma, to keep that in mind, sigma sub SR is the acquisition manifold. Just to keep it in mind. There won't be too much new notation, but just in case, that's a new one for us, so we can keep it in mind. All right, so we have this map. E. It's the scattering operator. It sends the sound field, the sound scalar field in the subsurface of the Earth to our pressure measurements for pairs of sources and receivers and various time values t. A couple of really common. Let me try and make that a little bit. Yeah, let me come out of this for a second and make it a bit bigger so you can see those pictures. So those are two really common acquisition manifolds where you have a single point source and an interval of of receivers or an area of receivers if it's 3D. This is the 2D situation. So you have a single source, and in geophysics that's known as the common shot experiment. Okay, so the sigma sub SR consists of a single point source and then an interval or an area of receivers. So some codimension 0 set on the surface for the receivers. And the other one, which used to not be as common, but it is actually employed on occasion at least, where you allow yourself to have a similar kind of set of sources. So codimension 0 set of sources as well, right? So full data set, or kind of like a deluxe data set. It's very expensive actually. Right?
So they're both two-dimensional, S and R?
Yeah, so the open set of sources would be, if it was three-dimensional Earth, right, this would be two-dimensional and this would be two-dimensional. Yeah. So very expensive from the point of view of computation, but whoops. I don't know. Let's see if this fixes it. Yeah, okay. All right. So the goal, as I said in the cartoon earlier, is from our pressure measurements, right, on the surface, on the acquisition manifold for an interval of time, is to solve the inverse problem and invert E, figure out what C is from these pressure measurements. Okay, so that's a fully nonlinear inverse problem. In practice, really what we're after is trying to figure out what the high frequency components of C are. So where are the jumps in sound speed between different types of rocks, for example. So as I said, that inverse problem is highly nonlinear with respect to the coefficient C. Right. Look at the wave equation. C enters in here as a reciprocal square. Right? It's not going to be a linear response to a change in C. So what we do is exactly what we did in the radar problem. We linearize the problem. So we linearize about a background reference field, C0. Right? That was the speed of light in the radar problem, constant. In this seismic problem, it's going to be a very smooth variable sound speed, which is obtained by all sorts of different processes, which I'm not going to go into. It's another talk in itself as to how you estimate this background field. And then delta C is the high frequency perturbation. That's the thing that contains things like the Heaviside function for switches between two different types of velocities.
Did you still going to talk about how to recover C0 also? No.
And tomorrow's talk I will mention.
Okay.
Yeah.
Is C0 a constant?
No, it's variable. It'll become very clear soon. Yeah, this is going to produce bending waves. Yeah. No, our rays are no longer straight lines. And P0 is the solution to the wave equation with C0 written here. Right? So sort of the self-explanatory notation. So P0 is the Green's function in the smooth background field C0. So this corresponds to this. And then this is the singular or high frequency component of the pressure field that we record at the geophones. So if you do the formalized linearization process, then that perturbed pressure field satisfies the wave equation with the background sound speed, and its source is again some sort of interaction between the perturbation in the sound speed and the background propagating field. So you remember the similarity between the radar problem? In the radar problem, when we linearized the problem on the right hand side, we had minus v dt squared times the background propagating field. So there was a very, very similar type of expression. Some sort of interaction between the delta C, which is causing the scattering, and the background field. Right, so that makes perfect kind of physical sense if you look back at the picture. These are kind of like the delta C's, and you've got this background P0 coming down and interacts with the delta C. So delta C and P somehow are giving rise to a source of a reflected wave, and that's exactly what we see in the PDE. This is the right-hand side of the linearized PDE, so that's our source for the reflected waves. Okay. So I have this interaction between the background propagating field and the perturbed coefficient. All right. So of course, what we're going to do is talk about the linearized problem, really. So E now gets replaced by F. So this is the linearized scattering operator that takes the delta C coefficient in the source here and maps it to the solution of this wave equation. Okay. And that is, by definition, linear, right? We've made it into a linear dependence here. Okay, so that's the linearized scattering operator F. So that's our reflection operator. That's the analog of a reflection operator from the radar problem that we studied for the previous 2 lectures. Okay. Is it okay so far? I'm happy to go back over. I don't want you to get lost right at the start. Any questions? Is it okay? Okay. Yeah? Your question? Okay. So the linearized inverse problem, IP's inverse problem, is for a known C0, right? That's known. Right? I think that's worth writing down. Don't get confused. C0 is always known in this talk. That's what Rakesh was asking about. I'll say a little bit more about what to do if you didn't know C0 tomorrow. Okay, so let's just concentrate on finding delta C. Right, so the forward map, or the linearized scattering operator, maps delta C to the excess pressure field, high frequency pressure field at the receivers. And the linearized inverse problem is to go in the reverse direction and try and estimate delta C from our excess pressure measurements. Okay. P0, by the way, is the Green's function corresponding to C0, so it just means that 1 over C0 squared dt squared minus Laplacian of P0 satisfies the wave equation that we had at the start with the C0 coefficient. Okay, so that's the P0 that's appearing here. That's the background field. All right, let's have a preview of what actual seismic data would look like. Imagine you had a constant sound speed V0, V for velocity, not to be confused with the reflectivity function from the radar, right? So here is a central point, and here's the origin, and here is a receiver location, a general receiver location, at a distance r away from the origin here. So suppose this reflecting material is at a depth z. If you just use Pythagoras' rule for just travel times, right? Use this right angle triangle and double your result, you'll end up with this relationship between travel time and the distance, or the half range distance to the receiver location r. Okay, so if you were to square that, you would see that it's a hyperbola. Right? So what you expect is if you send a little wavelet off from the source, it travels down, more or less is keeping the kind of shape. It might be spreading out a bit, deforming, but let's not worry about that kind of detail. The point is, as if you move further and further away from zero, so if you increase your receiver location, it's going to take longer and longer in time for you to hear that echo come back, according to that formula. Right? That's the so-called hyperbolic move-out. Okay, and you see that in seismic traces. It happen going to the left rather than going to the right. So this is, again, across the horizontal axis, you'll see receiver location, and this is time milliseconds going down. Right? And so experts in the area will look at the actual data and be able to make comments about what they think is in the subsurface based on these events. Right? They're all on top of each other, and these are the kind of hyperbolic move-out curves from multiple reflectors or possible multiple reflections between the surface of the Earth and the same reflector bouncing up and down. Okay, so there's a lot of stuff in here. And the reason I'm showing you a seismic trace, well, is first of all, it's nice to see one, I suppose. But what I'm going to show you is that there's very, very weak mathematical theory, but there's at least some data justification of linearization. And I took these from a very nice kind of survey technical report by Bill Symes. I have the reference at the end of the talk. And
Can you explain the axis, please?
yeah, so these are, it looks as though you're traveling further and further away from the receiver distance is increasing as you move across this way, and time is traveling down. So you can see it's taking longer for a further away geophone. It's taking longer in time for you to hear the echo coming back. Okay, so this would be the result of the nonlinear scattering operator E.
So could you tell from this where the delta C is, or vaguely? So
that's what I'm saying. The experts will look at it and they'll say, well, there looks like there's an event here. It looks like there's a reflector at. If I have a rough estimate of the speed.
So could you tell me what it is?
No. You call my bluff? Yeah, no, I'm not. But I'm sure there are people. The person behind you might be able to tell you. Okay. This is the linearized seismogram. So this is the output of F. Well, that's it's worth doing. They're almost on the same scale, I think. So you can see there's some stuff after disappearing.
So what is the second slide you showed?
This is the linearized seismogram. This is the output of F.
And that was the nonlinear one.
Yeah, so this is the output of E, the nonlinear scattering operator. This is the output of F, which we're going to study for the rest of the lecture.
Okay, and what is the C0 and delta C and stuff? You don't know that. Okay.
No, I cannot remember.
Okay.
This is the difference. One seismogram subtracted from the other. And the interpretation, I'm asking you to believe me. I at this stage, I do not remember the details. But apparently it is fairly convincing that this difference is explained by multiple reflections. Right? So, what I mean by multiple reflections is here's your source, here's maybe a interface between two different types of materials. Right, so you might see the wave after scattering multiple times by the time it gets to a geophone. And that type of thing, that multiple type of scattering is not accounted for in our linearized model. Okay? Alright, so let's do the same type of program as we did for the radar and develop an integral transform representation of the data. Okay? And rather than do the same type of program as we did for the radar, which would be pretty boring to repeat all the same kind of details, I'll show you a different technique for developing the model. Right, so here's our excess pressure field associated to source, location, receiver location, and time. And that very first line is a tautology. Right? It's just evaluating using the delta functions. Okay, so this x in here will be set to r, and this t prime in here will be set to t. Right? It says nothing. So it looks a bit crazy. Why would you do such a thing? You would do such a thing because this pair of delta functions can be viewed as the background wave operator. So this is the background inversion, right? The wave operator. So, according to the definition of the background Green's function, this wave operator acting on P0 should have exactly that type of source. Okay? So I put it in. I do integration by parts, hiding fairly significant few details. Right? This is got a forward light cone. This one's got a backward light cone. And so you need to figure out where the intersection of the supports are and convince yourself that there are no boundary terms picked up when you do integration by parts. But it's so. Okay? So I'm going to simply, because it's second order, I'm just going to simply transfer the inversion onto delta P and replace a box 0 on delta P by the solution. Its source, remember, its source was this quantity here. I may have left off a minus sign. I can't remember. Do you remember? Let me just remind you. There, I left off the minus thing. This is box 0 applied to delta P. It's that. Okay, so I'm just inserting it. Here. Okay, so now the next thing to do is to make some progress, we need to figure out an expression for P0. Right? And when we were in the radar case, we had a constant speed of propagation. The C0 was just the speed of light. And you remember in the radar case, P0 would have looked like delta of T minus X minus gamma of S over C naught. Right, a spherical wave centered at the location of the radar at its current location, gamma of S, with the flight track. You've got this radar flying across the sky at a current location, gamma of S. It emits a spherical wave, and you've got this delta function, and then there's over 4 pi distance between X minus gamma of S. Right, this geometrical spreading factor that accounts for the energy being spread over the wavefront. We don't have that luxury available to us in this situation. We don't have a constant C0 anymore, so we can't write down such a simple closed form expression for the fundamental solution P0, or the Green's function P0. So what we're going to do is, if there are no caustics, I have a problem. I haven't explained what caustic is yet, but for the moment, I think about caustics as let me show you a picture. It's on the next page. Here is the source. There is a low velocity lens in here, so I think it's not shown explicitly. I want to show you the ray structure instead. There's a disk, roughly where I'm tracing with my finger, where the velocity has got a negative bump function. So the velocity decreases smoothly in a circular region. And rays, satisfying Fermat's principle, to take the shortest path, will bend around that, along the contours, like so, either side of the disk. And can you see your eye picking out this envelope of rays here? There's a cusp. So there's a cusp shape here. There's a cusp curve. On each point on that cusp curve, there's a ray tangent to it. So this is an envelope of rays. And that's an example, a prime example of a caustic. Right? So just before you reach the caustic, if you tell me the travel time, how long the ray has traveled, it's a nice, well-behaved function. It starts to become a singular function as you reach the caustic. And beyond the caustic, it becomes multi-valued. You see where my fingers are? Here? There's now 3 travel times passing over that point. Okay, so for the moment, what you can think about in terms of a caustic is the onset of a wave that is focusing. Okay, I'll define much more precisely tomorrow what a caustic is. Okay, so the reason I'm bringing that up is, if we do not have any caustics, so if we don't have any focusing of waves, think about C0 as being close to a constant maybe, but not necessarily a constant. And then we can use a classical approximation for the Green's function called the geometrical optics approximation. I'll say a few more words about that in a minute. And then there's a more sophisticated, kind of souped up version of that, if you allow caustics into the scenario, and you have to use a more sophisticated asymptotic approximation. It's called a uniform asymptotic approximation. Okay, so we're going to have 2 types of regimes that we're going to, 2 asymptotic types of approximation that we're going to plug in for P0 here and here, depending on whether caustics are there or not. Okay. So, let me say a few words about rays. Rays are the orthogonal trajectories to the wave fronts. Right? So you have, in fact, I had them right here. Right, they were on this picture earlier. There. So these are the wave fronts, and here's an orthogonal to the wavefront. Right? So these are the rays. All right. One of the ways that we're going to get over the problems that caustics form is it's no good just tracking a ray by how much time has elapsed to figure out which ray that you're on. Because as you get to some point like this, beyond the caustic, there are multiple travel times. So to distinguish which ray you're talking about, you want to talk about what's known as the slowness vector. So it's basically a vector which is got the same direction as the velocity of the ray, but its speed is the reciprocal of the sound speed. Right? There's a reason for that, a good reason, but I'm not going to get into it. So nu is the velocity of the ray. S is arc length, so this is a unit vector, and you take that unit velocity vector and divide it by the speed at that point on the ray. Right? Again, gamma of S is the parameterization of the ray. Okay, and this is just a preview. We're not going to do anything much with this idea just for the moment. We will be doing something with this tomorrow. The collection of points on a ray together, so this point, together with its slowness vector, if you take the collection of all those points and their slowness vectors together, they form a Lagrangian submanifold that we talked about in yesterday's lecture. Okay, so we'll be making use of that tomorrow. Right? It's basically, if you think about solving PDEs, nonlinear first order PDEs, these collections of points and their slowness vectors are the bicharacteristic strips of a certain PDE called the Eikenal equation, which we'll see in just a few minutes. Okay, so here's the geometrical optics approximation. If there are no caustics, no waves focusing, then the leading order approximation for the background Lagrange function is a delta function delayed by a travel time function that tells you how much time it takes to travel between the source and the scattering location in the subsurface X. Right? So you see the similarity? Delta of t minus some travel time type function. Right? And then there's 1 over 4 pi distance, the spreading factor, is like the geometrical optics amplitude termed here. Right? So that's the similarity. And I'll tell you where that comes from, where these two functions, A and tau, come from in just a minute. So if you use that geometrical optics approximation in here, and do a very small bit of calculation, we don't have the time to do it, you'll end up with an integral representation of the excess pressure field basically being an amplitude which is like a product of two A's, one from the source to the scattering point and one from the receiver to the scattering point. And then you get another time shift here. So you get twice the derivative of the delta function evaluated at t minus the sum of the travel times. Right? So this is the total travel time from source to scatterer plus from scatterer back to receiver. Right? So these two terms here are time delay that give you this optical length in green. Right? So this is this distance between here and here. This is S and this is X. This is tau Sx plus tau XR. Right? So you get this time delayed pulse given by the correct time delay. Right? So it's physically plausible, even if I skipped over some of the details of the derivation. Okay, and you can see what you're doing is you're integrating delta C over a hypersurface. Right? You're looking at a level set. Travel time t equals the sum of those two travel times. Right? So if these travel time functions tau here were the old Euclidean distances here, you will be integrating delta C over an ellipsoidal surface. Right? T equal to a sum of two distances from two foci, S and R. Okay? So it would be an ellipsoidal transform if these were Euclidean distances. But they don't have to be, right? And so in fact what it's referred to, this got picked up the name due to a paper by Belkin. It's called a generalized Radon transform. So instead of integrating over planes, you're kind of integrating over deformed planes or surfaces. Okay. All right. So what about these two travel time function and geometrical optics amplitude functions? What are they about? So the idea where they come from is, Lax's kind of geometrical optics or progressing wave expansion type solution to PDEs with initial oscillatory data, given the reference to that paper at the end. What he does is he proposes an ansatz, an asymptotic solution for the Green's function is a sum of singular functions, so distributions, maybe like the delta function. So Sj, you sum over Sj, and you can asymptotically sum them appropriately. The important thing is that as you increase the index here, so j goes to j plus 1, Sj plus 1 is the primitive of Sj. So for example, if S1 was the delta function, then S2 would be the Heaviside function, and so on. S3 would be the function that is linear for positive side of the axis and 0 for the negative side of the axis, so forth. Okay, so that's just a proposed solution, right? And we kind of have seen that it's a reasonable solution, some sort of time-delayed solution with some spreading factor for energy. And if you plug that into the wave equation, right? So if you plug this proposed solution into this wave equation right here, this one, and collect all the most singular terms. So collect the s's with the highest index first, and look at their coefficient, and set that coefficient equal to 0. You will get that tau has to satisfy this equation, called the Eikenel equation. And if you look at the next most singular term, after plugging in our ansatz here into the wave equation over there, the next most singular term has a coefficient which is 0 when A satisfies this so-called transport equation. Not the transport equation from optical tomography that we saw, but more kind of a classical transport equation, transport of energy. Right? Amplitude squared is like an intensity. Okay, and actually, I was hinting at it earlier, S1 actually is the delta function, and it comes from matching the Green's function near the source, where the velocity is fairly constant in a punctured neighborhood of the actual source location. Okay, so that's what those two functions, tau and A, are about. So tau satisfies the Eikenel equation, A satisfies the transport equation, and there's a nice construction which will be relevant for tomorrow's talk. So this goes to caustics as well. So I get a better chance to explain a bit more what caustics are now in this diagram. This is so-called ray tube construction. You can read about it, a very nice discussion of it in Friedlander's Sun Pulses textbook. Again, the reference is at the end of the talk. So imagine you have an initial wavefront, right, with a little area, delta S1. And you let the rays, the orbital trajectories, travel forward in time, and after a certain amount of time, the wavefront has deformed to whatever it is over here. Okay, and think about a central ray in the middle here, the very thin ray tube. Right? And if you apply the divergence theorem to the transport equation, right, here, so imagine if you integrate this equation over the volume of the ray tube. Okay? Maybe this is worth putting up. And a very nice construction. Okay, so along the sides of the ray tube, since the ray tube is composed of rays, and the directions of the rays are actually orthogonal to the wavefronts, all these intermediate wavefronts as well. So the rays are perpendicular to the intermediate wavefronts, so the normal vector that you would have in the divergence theorem is going to be perpendicular to the rays. Okay, so we have nu, right, our little slowness vector pointing along the rays, and the normal vector in the divergence theorem is perpendicular to it. So if you apply the divergence theorem to the transport equation, you're going to get no contribution in the corresponding flux integral along the sides of the rays. Remember, we're integrating over the ray tube, divergence of a squared gradient tau is equal to 0. And so that's going to be the integral over the boundary of the ray tube of a squared gradient tau dot n ds. Right, and what I'm saying to you is in this flux integral, you're not going to get any contribution from the sides of the ray tube. And then the normal vector is pointing out that way, at that end of the ray tube, and out the opposite way, at the other end of the ray tube. So you get two contributions in the flux, one with a minus sign on it, and the result is 0. And if you read off what it says this. Right, for an little infinitesimal area, delta S1 and delta S2, this ratio is equal to this ratio. And if you rearrange it, right, just very simple algebra, what you see is this relationship between the two amplitudes at both ends of the ray tube. Okay? And now, if the rays are starting to focus and this ray tube is starting to close up, this delta S2 relative to delta S1 will start to go to 0. And this amplitude, A2, is going to explode. Right? That's the problem with geometrical optics. It's not valid in the neighborhood of acoustic. So you have to use a different approximation, the uniform asymptotic approximation that I mentioned earlier, which we're not going to go near for a while. Okay. Actually, we will, I think, fairly soon. In a few slides, we'll return to that. Okay. So that's worth keeping in mind. The geometrical optics amplitudes explodes at acoustic, so it's not inappropriate. Yeah?
But laxus ansatz is valid even when caustics are present?
No, not the way this is set up. No, you have to do something more sophisticated. Yeah.
So whatever that the asymptotic expansion that you wrote is for non-caustic.
Yeah, this one has got a travel time function. So the travel time function isn't even defined once you go beyond the caustic. Which branch of the wavefront are you on? Okay. So Lax will run into trouble there. Okay, so let's come back to the integral expression that we had for the scattering operator a few slides ago. It's just a rewrite. And let me do the same type of thing. Let me turn it into an oscillatory integral. Right? The two time derivatives will pick up on minus omega squared, so the amplitude will now depend on omega as well. Right? It's a cosmetic difference. And now, to come to your question, what do you do if you're going to allow caustics into the scenario? Remember I said that keeping track of the new vector helps you to determine which branch of the wavefront you're on, right? Which slowness vector you're on. So I'm skipping a whole bunch of details, but it's sort of plausible. If you're going to be able to use the slowness vector, I'm going to use a set of slowness vectors for the source wave, nu s, and I'm going to use a set of slowness vectors, nu r, for the reflected wave. So it's fairly believable, hopefully, that there is a travel time function that depends on these new parameters and an amplitude that depends on these new parameters for both the source and the receiver, and you superimpose the geometrical optics amplitudes over the various nu s's and nu r's. Okay? Now I'm asking you just to believe that, and because we do not have the time to go through it, and if you're not on acoustic, you can do a stationary phase reduction and it'll reduce back down to the geometrical optics approximation that we have here. Okay. Okay. And I suppose now the Eichner and transport equations now have to be solved in phase space, both a location and a direction. Okay. Right, but that can all be done. And I want to make the nu s's and nu r's, right? They're really only points on a sphere. I want to make them into genuine frequency variables, so they have to be able to vary in direction, and they have to grow very large. So I'm going to make a change of variables. Nu is going to be the temporal frequency scaled versions of both those direction vectors from the source and the receiver. Okay, so if you do that and make a change of variables, and I'm hiding a whole bunch of details, because we don't have the time to go through it, you're going to get slight change from this. Okay? It'll end up being some more complicated phase, some possibly more complicated amplitude. Right? Here's an A associated to the source, and A multiplied by an A associated to the receiver with the frequencies involved. But it works out. Okay, and this phi is a non-degenerate phase function. This is a classical symbol. It becomes a Fourier integral operator. And so that's a version of your 1988 result for the common shot experiment. Yeah, derived in a different way. But
Sorry?
derived in a different way, but
Yes.
it's not the way that you did it at all. But that's I hope that's at least plausible, even if I didn't show a lot of the details. Okay, so all the frequency variables now are psi frequency variables, or omega, and our direction variables from the source and the receiver. Okay, so that's our FIO representation of the scattering operator. Okay. All right. So I'll start a little bit to talk about imaging, but we're not going to get there today, really, I think, because there's a lot of stuff packed at the end of this lecture that I would like to spend a bit more time on. So, as we saw in the radar lectures, the name of the game for imaging is to apply the adjoint. Right? So we're going to do the same thing here. Apply the adjoint scattering operator to the data. All right. A little bit of history about what happened, I suppose, is appropriate. Belkin did exactly this for, where was it? Here. For this generalized Radon transform. He applied the back projection operator to that, carried out the back projection calculation in a way that's very close to the way that I carried out the back projection calculation in the first radar lecture. Remember all that change of variables with the it's very similar to what we did in the first lecture. That's what Belkin did as well. So, and he was able to show that F star F is a pseudo-differential operator, so you were able to faithfully image the subsurface, no artifacts. Okay, so whatever singularities in the subsurface are visible from your experimental point of view, right? Wherever you have the reflected waves available, the appropriate ones that are available, you'll be able to see the corresponding singularity in C, in delta C, I mean. Okay, so he did that for the common shot experiment under a very important assumption. No caustics are allowed from the source. Okay, let me go back. Picture. That's super important. So actually, I just skipped over there. No focusing of waves like that coming out of the source location. There's only one source in Belkin's experiment, in the common shot experiment. Right? So, if we only had one source, no focusing is allowed over here on the right-hand branch. Okay? Focusing as you go back up to the receiver, no problem. And that's sort of believable, right? You might have an ambiguity about which travel time branch you're on as you go back up to the receiver, but you've got multiple receivers to try and resolve things. Okay, so it's sort of believable that caustics should be allowed on the left-hand side. But not on the right-hand side, only one source. Okay, so that was Belkin's result in 1985. Where were we? Oops, too far. There. So F star F is the SIDO if you don't have any source caustics. Okay? But just making the point that receiver caustics are allowed. Right. Okay, so here's a kind of a precursor to what will come tomorrow. So suppose we're talking about the common shot experiment, right? The same experiment that Belkin considered. Okay? And if you restrict F to distributions that are supported in the subsurface region omega, say, right? So you've got some here are your sources, Here's your receivers. So I want to consider scatterers which are located in this subsurface domain omega. Okay? And the statement is that if you've got your scatterers restricted to this domain omega, then F maps this subloss space to this subloss space continuously if and only if there are no source caustics inside that domain omega. Okay? So the proof is, roughly speaking, using Garding's inequality and that blow up of the geometrical optics amplitude that we just went through in the ray tube construction. So here's a picture to try and illustrate what I mean. So you've got your omega somewhere around here. I'm taking a sequence of domains, omega 1, omega 2, all heading towards one of these kind of caustics. Okay? Meanwhile, the geometrical optics amplitudes in these domains is blowing up. And with the aid of that fact and Garding's inequality for the bonds of the FIO, then we're able to show that there will not be a continuous map, right? The constant, if it were continuous, degrades further and further as you approach the caustic. All right. So that's kind of an important result for imaging, because here's a consequence of it. F star F could not possibly be a pseudo-differential operator if you allow source caustics. Okay, so that's why Belkin needed to rule it out. And the reason is, if we just use this definition of the adjoint, right? Here's the norm of F. Here's the norm of the data. I didn't say it earlier, but it's a fact that the pressure field naturally lives in L2, right? And this FIO has got an order of 1/2 in this scenario in a two-dimensional setting. So delta C should be in H1/2. Okay, so this would be the appropriate bracket pairing with F delta C, comma F delta C, and then I pop the F star over to here, so it's going to be a -1/2 pairing. Okay, so F star F warrants to the differential operator. They don't have that type of change in property of boundedness. Right? They're either bounded or they're not. There's no change in character. Do you remember? I can't find it. It's going to be in lecture talk number in the radar number 1 lecture. Well, I said something along the lines where F maps the subloss space HS to HS minus P, the order of the FIO, minus K, and K had something to do with the geometry of the wavefront relation of the FIO. You've got a very, very specific handle on what kind of K there is for a pseudo-differential operator. It's the diagonal wavefront relation, and there's no doubt about whether it's going to change its a property about being bounded or not. It is bounded or it's not bounded at all. There's no change in character. So, yet we have a change in character here, depending on whether we allow source caustic into this scenario or not. So it could not possibly be a pseudo-differential operator. Guess what it's going to be? It's going to be an IPL type class in a lot of cases. And okay, so I'll show you one scenario tomorrow for a specific type of caustic where F star F belongs to one of the IPL classes. Okay. I think that's actually a very good place to stop. So I'll save the imaging part of the talk for tomorrow. Any questions? Yeah.
In practice, how is this C node? Is there?
How do you get it?
Yes.
Okay.
Substantial investigation of the ground.
Tomographic experiments.
Okay.
One possibility. These types of models with the Marmousi type data set, well, they basically do kind of a convolution and blur to make it a smoothed out version of it, and that'll be the C naught. So you can do modifications and convolve with some smooth compatible support function. There is not a unique answer to your question. You can still potentially solve the problem with different C naughts. Okay, so you have a trade-off between delta C and C naught. You could push some of the dependence on C naught into delta C, but not.
You just multiple experiments. So start with some guess and then do something of the kind you described and get the better.
Oh yes, okay, yeah. So that was kind of Rakesh's question earlier. Tomorrow I will talk about a strategy for estimating C naught using a kind of a regularized least square fit.
So you basically get C0 and delta C together.
Simultaneously. Yep, so you have an iterated loop. You start with a guess for C naught. You do the back projection and get your image.
So you get
And then you do your new fit, and you keep on bootstrapping your way up to trying to do the fit. But it's full of problems. Very difficult problem to solve. That's the velocity estimation problem you're asking about. Any other questions? Thanks.
very much